Hi everybody. Right now we're doing a review of Unit 4. This review number 4 corresponds to Unit number 4 on exponential functions. And just a reminder, watching these videos is not enough for a review. You need to do practice on your own to make sure you understand all the material. I'm sure if you go through these videotape reviews and you do the review booklet which I gave to you and you redo your test, you'll be in fine shape for the exam. Now this will go blurry for a few minutes, but I just want to make sure it's as focused as it can be. There you go. Okay, let's review the 10 exponent laws. You learned most of these in grade 10, but let's go over them. When you multiply two powers with the same base, you know you add the exponents. When you divide two powers with the same base, you know you subtract the exponents. Rule number 3. Here we have a power to a power. When you have a power to a power, you multiply the exponents. When you have a product to a power, then you know that exponent applies to everything inside these brackets. That's a to the n, b to the n. 4. Let's see, sorry. I didn't count very well here, so let's just correct that. That's 4 and 5. Number 5. Now we have a rational expression to a power, and it's all to that power, so you know that exponent gets applied to the a as well as to the b, which is the denominator, a to the n over b to the n. 6. A to the 0, you know that any base to the 0 is equal to 1. Rule number 7, a to a negative exponent, we simply reciprocate the base. Okay, let's start up here. Rule number 8, if you have m to a fractional exponent, that's n over m. Let's see, I'll put the m on top and the n on the bottom. Oh, I don't like the way I wrote that. We better have a different base here. That should be an a to the m over n, a to the to the m over n. So that would be, the denominator makes that the nth root of a to the exponent m. This could also be written as the nth root of a all to the m. So that was actually rule number 9. I skipped a rule, so let's get rule number 8 up here. A to a fractional exponent is equal to the nth root of a. Now if we have a to a negative fractional exponent, we simply reciprocate it. This would equal 1 over the nth root of a all to the m. Okay? That's a real quick review of all the exponent laws. I'm just doing that to refresh your memory. Okay, let's look at simplifying a few expressions just to get some practice. The first thing I would do is, well, we could simplify what's inside the brackets. Why don't we do that? Negative 3 minus 3, right? We have two expressions here with the same base. Negative 3 to the, that would be b to the minus 6. C squared, well, we've got to subtract the exponents here. C squared, c to the minus 5th. So 2 minus a negative 5. 2 minus a negative 5 is c to the 7. Okay, we still have that negative 3 there. So why don't we do this? Why don't we reciprocate this expression to get rid of the negative sign? So we have 3b, if we reciprocate it, that has to go into the denominator. So that would be 3 stays, that 3 comes to the bottom too. Everything in the numerator becomes the denominator. 3b minus 6, and that would be c to the 7, and that 5 would go on top, so that would make it a positive 3. So 5 to the exponent 3 is 125. 3 to the exponent 3 is 27. This is b. Negative 6 times negative 3 is negative 18. 7 times 3 is 21. And this is equal to 1. Notice the question asks us to express our final answer with positive exponents. So this is 125. I'm going to bring that to the top, b to the 18, divided by 27, c to the 21. So now this is as simplified as we can get it, and we're finished there. Okay, let's look at this example. Don't let the third root and the fourth root overwhelm you. There's nothing to get overwhelmed about here. We're just going to write it with fractional exponents. Notice I am using this law here. I'm changing from something that's using square root notation, right? And I'm converting it to fractional exponents. So the inside we have y to the 18 times x to the minus 3. That's to the 1/4, and that is to the 1/3. Now we have an exponent to a power, so that would make it y to the 18 over 12. X to the minus 3 would be minus 3 over 12. Reduce those exponents to lowest terms. Y to the 3/2, x to the minus 1/4. And now we have y to the 3/2 over x to the 1/4. That's our final answer. So just take it step by step. You know, there's more than one way of solving it. The important thing is you maintain bed mass throughout your solution and end up with this. Let's look at exponential functions and transformations. Well, let's just review this first. Just very briefly, you have a more detailed review in Unit 3. When we have an exponential function in this general form here, k x minus d plus c. Okay? Remember that A has to do with vertical stretches or compressions. And if A is negative and or reflections, depending, right? And or, I'll put the or there so it follows the and or reflections. Now K has to do with your horizontal stretches or compressions, and or horizontal reflections or reflections over y-axis. Over the y-axis. And this is reflections over x-axis. Now our D has to do with horizontal translations and C has to do with vertical translation. Let's do an example. We're going to graph this exponential function using transformation. So there's a little error here. There should be an x right beside that negative 1/2. So always remember factor k. Factor k. If you do not factor k, you won't get the right horizontal translation. So when we factor k, we get y equals negative 2. Our base is a half to the exponent negative 1/2 times x minus 4 plus 3. Always remember to check your work. You can always go back to make sure you factored correctly. So negative 1/2 times x is negative 1/2 x. A negative times a negative is positive, and a negative 1/2 times negative 4 is positive 2. And don't forget, don't drop that plus 3. So what we want to do is now graph. The first thing we're going to graph is our parent function, or our, if you want to call it, our basic function. So y equals 1/2 to the exponent x. That is our parent in this case. And I will graph that in blue. So 1/2 to the 0 is 1. 1/2 to the 1 is a half. 1/2 to the 2 is a quarter. 1/2 to the negative 1 is plus 2. 1/2 to the negative 2 is plus 4. 1/2 to the negative 3 is 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's our parent function. That's number 1. Let's now handle the reflection in the x-axis because of that negative in a vertical stretch by a factor of 2. So all the y values, right, the y values of this function will be multiplied by negative 2. 1 times negative 2 is negative 2. A half times negative 2 is negative 1. A quarter times negative 2 is negative a half. 2 times negative 2 is negative 4. 4 times negative 2 is negative 8. 1, 2, 3, all the way down to 8. And that should be enough for our graph. Okay, so that's graph number 2. Y equals negative 2, 1/2 to the x. And don't forget to label your x and y axis because that's important for communication. Now let's handle the k of negative 1/2. And I guess I'll draw that in black. Y equals negative 2, 1/2 to the negative 1/2 x. Okay. So this is a horizontal stretch by a factor of 2, as well as a reflection over the x-axis. So this x is 2. 2 times negative 2 is negative 4. This x is 1 times negative 2 is negative 2. 0, x value here is 0 times negative 2 is 0. X value here is negative 1. Negative 2 times negative 1 is positive 2. Negative 2 times negative 2 is positive 4. 1, 2, 3, 4. Okay, so now I'm just going to flip it around to draw it. And there we have it there. That is graph number 3. Now let's do the final graph, which is a horizontal translation of 4 to the right and up 3. 4 to the right and up 3, and I will do that in pencil. So translating graph number 3, we move it 4 to the right and up 3. 1, 2, 3, 4. See, that's the y value, there's a half. 1, 2, 3, 4. 1, 2, 3. One, two, three, 4. 1, 2, 3. Moving this point is, let's say I did that one, right? 1, 2, 3, 4. 1, 2, 3. No, I guess I didn't. 1, 2, 3, 4. 1, 2, 3. I better, oh, hold it a sec. I am doing the black graph, so 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. There we go. Okay, so now we can graph that in, and notice we have an asymptote which is characteristic of exponential functions. So we will draw that asymptote in there. So this is graph number 4. I'll just write it here. It's a tight fit, unfortunately. I'll write it here. 4 y equals negative 2 1 half to the 1 half x minus 4 plus 3. I apologize for the tight fit, but that's our final graph. This is graph number 4. And let's just draw our asymptote. We have remember exponential functions have an asymptote. Just let me draw that. The asymptote is y equals 3. Y equals 3. I'll just try to emphasize that again to make sure everybody in internet land can see this. There. Okay, good. That's it for that translation. It says describe the transformations in proper order. So let's do that. I might have to do that on a scrap piece of paper because it is so tight. Let's see what I can fit in here. Okay, when we describe the transformations in correct order, we just follow the order of the equation. So it's negative 2. That is 1, a reflection over x-axis. 2, vertical stretch by a factor of 2, and that our k value is negative 1 half, so we have reflection over y-axis. And we have a horizontal translation right 4. Oh, I forgot about for horizontal stretch. Let's see, we have reflection over x, vertical stretch by a factor of 2, reflection over y, 4, horizontal stretch by a factor of 2, and number 5 is horizontal translation right 4, and number 6, vertical translation up 3. There we go. There, I think we've done everything now. We graphed as a series of transformations. Here is our final graph with its asymptote. Remember, exponential functions have asymptotes. And we described the transformations in correct order. Okay, and we did that. All right, solving exponential equations. The basic theory behind solving exponential equations is, well, we can solve exponential equations when the powers of each side have the same base. is if a to the x equals a to the y, if the bases are the same, then we know the exponents must be equal. So let's try a few examples of solving exponential equations. Okay, here we want to solve for g, and g is part of the exponent g plus 2. So the first thing we're going to do is divide both sides by 4. So 6 to the g plus 2 is equal to, well, 144 divided by 4 is 36. Now we want to get the same base, so 6 to the g plus 2 is equal to 6 squared. G plus 2 is equal to 2. Oh, g equals 0. That's nice. Okay. Now this one is a little bit more complicated, so what we can do is factor out. We're going to factor out a common factor of 2 to the x. So notice 2 to the x times 2 squared, right? When you have the same base, you add exponents, so I haven't changed anything. This is x plus 2 minus 2 to the 3, right? X plus 3, always check, equals negative 64. So 2 to the x is equal to 4 minus 8, that's negative 4. We can divide both sides by negative 4, and we have 2 to the x equals 16. So we need to get the same base now, so 2 to the x equals 2 to the 4, so x equals 4. And then we had application questions involving exponential functions. So remember, the basic form of an exponential function is a at some time t equals the original amount, right? Some future amount equals the original amount, and k, we'll talk about what k is, to the t over d. So a at t is some amount at time t. A subscript 0 is the initial amount. Now, k equals 2 if doubling. K equals 3 if tripling. K equals 1/2 if it's a half-time question. K equals 1 plus I if I is a percentage increase. If I is a percentage increase. K equals 1 minus I if I is a percentage decrease. If I is a percentage decrease, such as depreciation. Such as depreciation. Let's do an example. This is a half-life question. I shouldn't call this half-time. Why don't we call this half-life just to be consistent here? Half-life, half-time. I guess it's equivalent. Radon has a half-life of 25 days. How much time does it take for a sample of 200 grams to decay to 12.5 grams? Okay, so A at time, some time, future time, is equal to the original amount that we have. It's a half-life, right? Half-life, half-time, so we use K is equal to a half. And this is T over D. So our original amount is 200 grams, right? And they're asking us how much time does it take? So to come down to 12.5, ooh, okay. So they're asking how long will it take to go from 200 grams to 12.5 grams? So that's our ending amount. And this is 1/2 to the t. Now, our half-life time is 25 days. Okay, so d equals 25. So the first thing we're going to do is go 12.5 divided by 200. Now, I don't know how good this calculator is at, but I just want to demonstrate it to you. 12.5 divided by 200, and that equals 1 over 16. If you wanted it in decimal version, you have that, but in fraction, so it's good to use your conversion button if you want to get it to a fraction. So this is 1 over 16 equals 1/2 to the t over 25. So notice we need, in order to solve this equation, we need the same base. So we need to express 1 over 2. We need to express 1 over 16 to a base of 1 over 2. And you know that 2 to the 4 is equal to 16. Now we have the same base. We can equate the exponents. So t equals 100. Remember to write your conclusion. It takes 100 days for 200 grams of radon to decay to 12.5 grams. And that's it. Nice short little review for a short little unit on exponential functions.